Hi guys, it is week 3 on the monthly challenge. So let's quickly go through setting working directory and importing environment. As a next step, what I'm to do is I'm going to analyze official data on air pollution. As a very first step, it makes sense just to check variables class. In particular, what I do is I check the class for PM10 concentration and also the time variable. You might note that the time variable is character. As the next step, I would fix it. For this purpose, once again, I would use the Lubridate library. Basically, the time zone is East European. And as you might note, now the class is correct. So moving on, the next steps I do is just generate a time vector with hourly sampling rate. Okay, the next thing is actually to create time series using official data on PM10 concentration. Okay, and finally I am to bind data for 2017 and 2018 for every station. So let's just quickly do it. Okay, and now in the list TEU is collected information for 2017 and 2018 on the 5 official stations we have. Okay, as a next step, it is important to check if any duplicates are recorded. Yes, we have duplicates. So basically here you might wish to aggregate duplicated values, for example by averaging. However, for simplicity purposes, I would just remove them. Finally, I'm going to use the impute ts library in order to actually impute missing values. Let's just check their number and their number as percentage. So you might well see that the third station is characterized by 12% missing values. Let's just plot this. Okay, so basically you can see this period here of interruption. Therefore I will act safely using simple linear interpolation. So later on, when I am to interpolate the rest of the data, I will do it once again with linear interpolation. And so far we have prepared official data for further analysis. So as a next step, I'm just to add information on official air quality measurements to the dataset of every geo unit as defined during week 2. First, what I need to do is unify time zones. So I'd like to pay attention that due to the fact that there is a transfer from winter to summertime, there should be one NA value introduced, so I'm to remove it. Okay, as soon as time zones are unified, so what I'm just to do is I am to identify, okay, what is the first day of observation for every official station. So here you might see, for example, the first station is being observed firstly on the 28th of November 2017, and the last observation is at 14th of September 2018. So this information is important, especially when we are to interpolate data. Okay, now I'm to merge data on air pollution for every geo unit with official measurements by stations. So I'm doing this by using the left join function. I'm doing this first for the very first available station, and then I do this repeatedly for rest of the stations. Okay, so now you can view, um, for example, let's say the very first element of this list. It is a data frame on the first cluster. So what I have here is time, cluster ID, elevation, values of citizens, measurements on air pollution, temperature, humidity, pressure, and here are data for the official stations. For example, if you have a look at the second data frame, this is the cluster corresponding to cluster ID 22. As you can see, records for this cluster starts earlier than records for official stations, so we should keep this in mind later on. Okay, so let's just move down the script. Just clean up actual auxiliary information. Now I'm to interpolate missing values for P1 variable. This is the citizens um, measurements on air pollution. First I would do preliminary analysis, so I would calculate descriptive statistics for the four variables. This is from the citizen dataset. This is P10 concentration, temperature, humidity, and pressure. And then I'm just to visualize results. So here what I have on my picture, on the first picture, is percentage of missing values for the P1 variable. Then you have percentage of missing values for humidity, temperature, etc. So I should know that talking about humidity and pressure, some of the clusters are characterized by 100% missing value. So I should handle this issue during week 4, but now I am to focus solely on missing values regarding the P1 variable. Okay, so I am just to find clusters with more than 15% missing values on P1. Okay, so let's visualize data for these clusters. Okay, so as the next step is just to interpolate missing values, I should say that definitely whatever interpolation I would apply, this might affect the final analysis in case of those huge periods of missing observations. So I will approach in a really simple way this issue. I would just omit all these clusters out of my station just to make sure this would not affect seriously representability of clusters on the map. Okay, so red dots are actually the clusters I am to exclude from my further analysis due to more than 15% of missing observations on the response variable. So you might well know that still blue points are sufficient, and as a next step I'm just going to remove from the main list those clusters. And the next step is interpolation. Basically I'm going to use linear interpolation. Here is another alternative you might wish to use that is also well suited to this type of data. Okay, and now we can move on with step 3 of our analysis. In fact, step 3 is design of decomposition procedure. So basically my idea here is to split data into signal and noise. For this purpose, I would use a really simple approach of applying linear regression analysis. Of course, you might approach this task in different ways. This one I'm to present here is really rough decomposition, but I think it suffices for illustrative purposes. So I am to start with creation of correlation matrix. So let me just open this structure and explain what's here. So basically, here you might see as a row the cluster ID. And for example, this correlation here is the correlation between citizen science measurements for air pollution for cluster 22 with measurements for the very first official station. Okay, as you can see, for the first cluster, the maximum correlation recorded is 62%, and it is with the third official station, this one. Okay, so this is important information because I'm going to estimate linear regression with just one explanatory variable, and the explanatory variable would be official air pollution measurements at the official station with highest correlation. However, I just want to make sure that actually all of the clusters are sufficiently well correlated with at least one station. So here what I am to do is I'm just to visualize correlation results by official stations. So for every official station you have correlation measures on air pollution with different clusters. Okay, so you can see that there are clusters definitely weakly correlated to official data, so I'm not going to analyze them further. Okay, I'm to adjust clusters um, with correlation that is at least 75% with one of the official stations, so that's the next step in my analysis. So I'm making a subsample, and you can see that this subsample contains 55 clusters. So at the end of this video I'm going to suggest an approach for the rest of the clusters, but now let's stick with this idea. Yet once again I need to see what's going on with um, representation of further analyzed clusters on the map. You can see that the red dots actually, okay, yes, the red dots represent clusters with 75% or more correlation with at least one official station. So you can see fine representability at the map. Okay, prior to running linear regression, what I really need to do is I need to make sure that we have just a second. Just let me close all these windows. And let's make a clean window. Okay, so what I'm to see here is the augmented decay Fuller stationarity test confirms stationarity at 5% level of significance for all of the time series but one. Once again, you can see that the p-value is less than 10%, yet I'm just to have a look at the autocorrelation function of this time series. Okay, so it suggests stationarity, therefore I'm pretty sure the time series I'm to analyze are stationary, so I could run linear regression now. I would do this via collecting individual equations into list. So uh, for all clusters that are further analyzed, I would take the interpolated values and also the station with the official data for P10 concentration for the station that is most correlated with this value. Okay, so let's run this equation and just clean up auxiliary information. Okay, now I'm just to summarize the most important information out of these equations, and I'm just going to go through this table. So here in the equation summary table I have the beta estimate corresponding to the impact of measurement at the selected official station. You can see that the statistics are indicating significance of estimates, so I might move on with adjusting data. So let's quickly visualize this result. It's always a good idea. Okay, so you can see that all p-values are really close to 0%. Also, coefficients make sense, so they fluctuate between 0.6 and 1.6, so we don't have any unexpected or extreme values, so everything seems fine here. So as a last step, I'm just going to add an additional information for all 55 clusters subject to adjustments. So for example, you can see the result. For example, this cluster is with adjusted values. So basically what you can see is that for the initial months when we have no observations on official stations, we have also no adjustments. So adjustments starts as soon as we have observations on the official station, and also the end date is selected in the same manner. So here is suggestion on actual fitted. Okay. So the black points indicate actual data, and red points indicate adjusted data. So in this particular case, let me just quickly view the correlation. So talking about cluster 74, the maximum correlation is 78%, so it's fine fit. That is, the adjusted R square is actually 0.78 at the power of 2, so the R square is 60%, so it's not the best fit, but what you can see here is red points stand for adjusted data, and we have the same results talking about rest of the adjusted cluster information. So now I have a suggestion on how we could possibly treat the other stations that are excluded out of this analysis. So once again, if I am to show this on the map, okay, now what I'm going to briefly explain is a possible suggestion on how to adjust clusters corresponding to blue points. Okay, so here I would use information on elevation, and I would create an auxiliary matrix, an auxiliary data frame, where the first column is average data on interpolated values for air pollution measured by citizens, and the second column is elevation. So as next step, I just fit a simple regression equation. So let's have a look at its summary. Okay, so here it is. Basically, as this value is statistically significant, we might use it later on as a correction factor through identifying the closest station with adjusted values. However, we should be really careful due to the fact that the fit is really poor, but that's just an idea. Of course, this is quite involved issue of adjusting data, and here for simplicity purposes, also for educational purposes, show really simple techniques. Hope this was useful, guys. Bye bye.